not the history?
You can just go to the website actually, and then on the
Yeah, no, okay. I'll look.
there's a tab like history or something.
Yeah.
Are you posting this online in YouTube or so? Because I just saw the recording.
No, it will be uploaded later to YouTube.
Okay.
At least that's the idea. I mean,
Yeah,
everything goes well.
If you wanted to put it to YouTube, I don't care. I'm up to you.
Okay, so I'm stopping your sharing for the moment, and I'll just say
Sure.
Yeah. Okay. So this is the an honorable history of the Couette-Taylor meeting, what it's called now, the International Couette-Taylor Workshop. You see, it's been held roughly every 2 years ever since 1979, which is pretty impressive. No breaks, like very few. And this is by coincidence, this is the 21st edition of it, and it's also being held in 2021. The next one we believe will be held in 2023, and we're taking candidates, or somebody is taking candidates for who will host it. I'm thinking it should be held in the UK. It's the anniversary of Taylor's paper, 1923, so it's a big deal, but it could be held someplace else. Anyway, this is the long and honorable history, and those of you, who have been attending for many, many years, sometimes amuse myself by trying to recall this list from memory. I've been able to do pretty well. Okay, so that's the end of the chatting, I think. I will now go back from sharing.
So, Lorette, were you saying that the next one should be held by the G.I. Taylor professor then?
Yes, and who's that?
I don't know.
That's true. We should contact that person.
Yeah.
Okay.
I don't know if he's here, but otherwise yeah.
Okay. Anyway, it will be held in 2023. It will be the 100th anniversary. I mean, and hopefully, as I said, in the UK, which seems appropriate, but maybe not. Maybe it won't. Okay, so I'm going to stop sharing. Is that okay? And here we have Mark Avila, who is going to be giving the first talk. He's going to start in 2 minutes. And I guess, let's see. Maybe I'll start the introduction here. I've known Mark Avila a long time because I was on his thesis committee, and that was at Barcelona at Catalonia, which is one of the great centers of Taylor Couette work. We have many participants from that great institution right now, Sebastian and Alvaro and Paco and maybe others. And so I knew him then, and then after that he went to Göttingen with Bjorn Hoff. You'll correct me if I'm wrong, Mark. And then he went also to Austria with Bjorn Hoff when he moved there. No, he went to
Erlangen. I went in.
To Erlangen. Okay. You never went to Austria. Yes. Okay. You went to Erlangen, and then after Erlangen, he went to Bremen. And he is responsible for the balance. That is, otherwise there would be an imbalance because Mark is from Catalonia, from Spain, and he is working in Germany. And Sebastian Altmaier, one of our organizers, is from Germany. Am I right there? And he is working in Catalonia. So, got to balance these things out, or otherwise the universe would be perturbed. Our third organizer is Sander from Twente, another great center of Taylor Couette work. And you'll be hearing more from all of us as we go along. And now I think it's time for Mark Avila to give his talk. Thank you, Mark.
Yeah, thank you, Lorette. That's really punctual. I'm surprised. I thought you would be speaking first at 12. I'm really happy to start and have my 25 minutes time in full. So I guess you can see my screen properly now. Does that work?
Yes, perfect.
And you can hear me also well. I don't need to put
perfect.
Perfect. Okay. Wonderful. So I like it, Lorette, that you started speaking about the history of Taylor Couette workshop or Couette-Taylor workshop. I remember my first one that was back in 2005, and I had been a PhD student just for 9 months, and I was still struggling with spectral methods and learning bifurcations and about Taylor Couette flow. And then Professor Takeda held this great conference in Sapporo in Japan, where we had a lot of fun. And then later in Le Havre with Innocent Mutabazi, who took great care of us. And today, online, I'm really sad to give I'm very happy to give an invited talk. I'm sad it's online because I would really like to meet all of you after these years. And especially today, I will be talking about Taylor Couette flow, which is maybe not the center of my research right now, but together with Daniel Feldman, who's a postdoc, an excellent postdoc in my group, we've done this work also with José López and Juan Pedro Mellado at the Polytechnic University of Catalonia that you just mentioned, and then with Michael Wilczek in Göttingen, who works on Rayleigh-Banach convection. So I'm going to speak about Taylor Couette flow and Rayleigh-Banach convection, and if they are twins or not. And with this, with this short introduction, I would like to start on the topic. And I put here the one sentence that everybody working on turbulence like to use. So turbulence is ubiquitous in nature and technology, just because the Reynolds number is very high in most cases with which we are focused, except maybe in microfluidics. And now turbulence, as you know, is a non-equilibrium phenomenon. You must fit in some energy so that turbulence can survive. And the way you do this, it's quite different depending on the setup. In many cases, you do this by temperature difference or density difference, by buoyancy. We can generate turbulence because light particles or parcels will go up. And then also if we have strong velocity gradients, strong shear shown here in the second and in the third examples, by having large shear, large velocity gradients, we can generate turbulence. And of course, the question is how universal are the properties of turbulence depending on the driving that we use to generate it. And if we think about small scales, I think most of you will agree that thanks to Kolmogorov and many others, we know quite well that at small scales, everything should be universal. And we expect that, of course, large scales, due to boundary conditions and geometry, things are quite different. And in this sense of seeking for universality, I think that Rayleigh-Banach and Taylor Couette flow are two very interesting systems in which we can study turbulence driven by temperature gradients and driven also by shear. Here, because we have a fluid between two rotating cylinders which rotate at different angular speeds, and with this shear, turbulence will be generated. And we have here an analogy, as you can see, between temperature difference and difference in the angular velocity. We have in the Rayleigh-Banach mainly one single parameter that governs the system besides the geometry. That's the Rayleigh number, which we can vary by increasing the temperature difference, and then the Nusselt number, which will characterize how strong the turbulent transport is. And for the Taylor Couette flow, I think typically in this conference, the beloved parameters, the most famous ones, are the inner Reynolds for the inner cylinder and the inner Reynolds for the outer cylinder. And as a response, the torque that we need to drive, for example, the inner cylinder, which here is normalized by the torque required to drive the laminar flow, the circular Couette flow. And then we get a Nusselt number analogous to the one for Rayleigh-Banach convection. So the analogy that these two systems are analogous or similar is well known for a long time. And I want to point out here to a paper by Friedrich Busse, and he highlighted Taylor Couette experiments of the Twente group and also of Dan Lathrop, where it was shown that the scaling of torque was identical as in Rayleigh-Banach. Now, that these two systems are analogous or similar was pointed out already by Jeffries, and here's a quotation where he says Taylor and Lowe have suggested that there should be an analogy between the conditions in a liquid, in a layer of liquid heated from below, and a liquid between two coaxial cylinders rotating at different rates. And indeed, what Jeffries showed, and this is done also seen in the Drazinbukh and Chandrasekhar, is that for the case of narrow gap, so Taylor Couette with a very, very narrow gap, then we get rotating plane Couette flow, and rotating plane Couette flow has exactly the same stability properties as Rayleigh-Banach. So this was, in this sense, an exact analogy telling that the linear stability of rotating plane Couette can be deduced from that of Rayleigh-Banach convection by a simple change of parameters. And this is regarding the linear stability. Then, as you know, at the root of this conference, Taylor Couette conference, we have the chaos and pattern formation community, and a lot of analogies between the transitions and bifurcations that occur in the two systems was investigated in the 70s and 80s mainly. Also there in the group of Sweeney, there were studies of Fourier turbulent flow, which now in the group of Lose, also like Bruno Eckert and others have been really advanced a lot, and where this comparison of transport, which I mentioned, was done, so that the transport of momentum scales like the transport of heat in the two systems, in Rayleigh-Banach and Taylor Couette flow. Now, to just show how similar these two systems are, I'm showing a picture of our direct numerical simulations. And in the left-hand side, we have here Taylor Couette flow at increasing Reynolds number. And in the right-hand side, you have Rayleigh-Banach convection for increasing Rayleigh number. And indeed, if you look at this figure, you will tell me, okay, I cannot distinguish them. I could not distinguish them either. So certainly these two systems are extremely similar also in the turbulent regime. And this was shown in what I think a really excellent, really nice paper that appeared last year. Exact relations between Rayleigh-Banach and rotating plane Couette flow in 2 dimensions by Bruno Eckert, Charlie Doring, and Jared Whitehead, in which they showed that the governing equations, that is the Navier-Stokes equation plus Boussinesq approximation for the temperature and heat equation, this set of equations is identical to the governing equations for Taylor Couette flow, or better said, for rotating plane Couette flow. That means under a parameter transformation, we can bring one set of equations to the other. And this means that these two systems are not only analog, but they are exactly the same system. There are, however, assumptions, important assumptions in this exact relationship. One is that this works only in 2 dimensions. Simply in 3 dimensions, the symmetries of the systems are different. Also, for the analogy to work, the Prandtl number needs to be set to 1, so that the viscous timescale is the same as the thermal timescale. And as I said, it works only in the limit of vanishing curvature, so rotating plane Couette flow, and in the really unstable co-rotating regime. So this sort of extends the analogy of Jeffrey, the exact analogy of Jeffrey for linear stability to the fully nonlinear regime, provided that these hypotheses here are satisfied. And as you see the paper here, when I look at it, I become very sad, and probably many of you. I mean, Bruno left us 2 years ago, and Charlie left us this year. So I think the talk would not be complete without having a second of remembrance for them in what is one of the last pieces, and certainly the last one that Bruno produced. And indeed, the paper came out after he passing away. So going back to the analogy, now we put the two systems here side by side, and we have analogy between the wall normal velocity or radial velocity in Taylor Couette and the span-wise velocity. They are analogous to each other. And then we have an analogy between the azimuthal velocity and the temperature. So we have here, we will work with in this analogy of Eckert and others. The equations are formulated in a frame co-rotating with the outer cylinder, so that in this frame the outer cylinder is stationary and the inner cylinder rotates at velocity u. Yeah, so we have here this boundary condition V0 and Vu at the outer and inner cylinder, analogous to the conditions for the temperature for the Rayleigh-Banach system. And then, so that this transformation works, or to decide how the one system becomes exactly the other system and the transformation, we need 2 key parameters. One is the Reynolds here, defined as the velocity of the inner cylinder in the co-rotating frame. That would be the difference of the velocities in the lab frame. And then we have also this rotation number, which is essentially the ratio of the rotation speed divided by this velocity of the inner cylinder. Yeah? So with these 2 parameters, and I cannot go, of course, into details here because I want to say something about our results as well. So we have here this analogy defined in the table. The velocity in the wall normal direction or radial for Taylor-Couette flow and the axial velocity or span-wise Banach convection, they transform exactly to each other. Then the deviation of the temperature transforms to a scaled deviation of the azimuthal velocity. As I say, the Prandtl number is exactly 1. And then that's maybe the key point, the Rayleigh, or one of the 2 key points, the Rayleigh number is equal to the Reynolds shear squared R omega multiplied by 1 minus R omega. So this means that a system, a Taylor-Couette flow with a given Reynolds shear and rotation number can be exactly transformed into a Rayleigh-Banach system of the Rayleigh number defined by this line here. And then, and that's the strongest contribution, we see that the Nusselt number of the Taylor-Couette flow, when we subtract 1 to eliminate the laminar part and scale it with 1 over, we scale it divided by 1 minus the rotation number, then we transform this into the Nusselt number of Rayleigh-Banach. So this fully characterizes the transport of the Taylor-Couette problem once we know the transport of the Rayleigh-Banach problem in 2 dimensions and in this Rayleigh stable corrotating regime. Otherwise, outside of this regime, of course, the physics change. For example, in counter rotation, and the analogy does not apply. So it applies only for R omega between 0 and 1, which is between outer cylinder stationary and the Rayleigh line. Now, so when and how does the analogy breaks down? That's the question we want to look at in this talk, and a couple of things more. So what happens when we include the effect of curvature? What happens when also we go to extreme rotation rates? That means extreme in the sense we go to the stationary outer cylinder, which is a singularity in this analogy, when we go to the Rayleigh line, which is the other singularity. And then also we want to look at 3-dimensional effects. And we do this by doing direct numerical simulations with these are 3-dimensional open source codes, which we use here in 2 dimensions. One is the code of Juan Pedro Mellado for convection, and then our code for Taylor-Couette flow. And because of the analogy, Rayleigh-Banach, it's quick to do. You just need to simulate a few Rayleigh numbers. And of course, to explore the analogy in Taylor-Couette flow, you need to scan a wide range of shear Reynolds numbers, rotation numbers, and also curvatures. So all of you that are in the Taylor-Couette, so here you can see, sorry, the effect of curvature just illustratively shown. Normally it is assumed in the turbulent regime, and there's a lot of work of the group of Twente and also of Eckhart showing that for curvatures or eta radius ratio of about 0.9 and higher, the effect of curvature is negligible for turbulence. And today we'll be looking at this number, but also at much smaller curvature, so 0.99, as we approach really the rotating plane Couette flow limit, which is the relevant one for the analogy. Now, what does this analogy do? Maybe in the community here, you are used to using the outer cylinder Reynolds number and the inner cylinder Reynolds number. And when you plot the analogy here, you see these curves, which are in orange color. And this means all the points in one of these curves have the same Rayleigh number and are exactly the same corresponding the governing equations. So under transformation, they are exactly the same. Yeah? And you can see this line going up by the inner cylinder, by the outer cylinder stationary here on the left, and then to the right approaching, collapsing into the Rayleigh line. And here you can see in the other representation that this rotation number also with stationary outer cylinder here, inner cylinder, and then Rayleigh line at the right. Yeah? And what you can see now, when you reduce the value of eta or increase the curvature, the Rayleigh line comes into the analogy. So to the right of this dashed line, the analogy does not apply simply because the laminar flow is stable. And as you increase eta, 0.83, 0.7, 0.5, the regime in which in principle we could apply the analogy gets more restricted. So what did we do to test the analogy just to see how good it is? That's a snapshot which I showed in the beginning. You could look at it and say you are happy. That's I didn't tell you before, but that's really very, very little curvature, eta 0.99. And indeed, if you look at a movie, there is not a movie, but a snapshot, you will see the dynamics are identical when looked in the appropriate time scale. Now, what we did is try something much harder, which Lorette Tuckerman knows very well. That's the Ekhaus instability. That is, we looked at how many states with different number of rolls we can achieve by playing with initial conditions and the history of the flow. And you can see here we start with the number of rolls, and then there are rapidly a lot of transitions until 0.02 viscous time units, and then there are more transitions until the flow settles into a statistically steady case. And we did this for a lot of parameters, and it's shown now. So you can see the stability band at low Rayleigh number in red for Rayleigh-Banach convection. Have a lot of states at low Rayleigh number. You can see that by virtue of the analogy, also for very small curvature, the curve is nearly identical, just shifted by a pair of rolls to the right, because curvature or eta 0.99 is not 1, and there's still differences. And as you reduce the curvature, or increase the curvature, sorry, a little bit, 0.91, you'll see that the band or the number of vortex states with numbers of rolls reduces a lot. So here, say from 8 until 16, and instead of 5 pairs to 30, which we had for very, very mild curvature. And as you increase, there is in agreement, by the way, with previous studies in the past, and as you increase the Rayleigh number substantially, you have access to much less states which are stable. And you can see also when you put curvature, more curvature into it, here with the black symbols, this gets reduced a bit. You can see qualitatively you get the same band, and there are some differences though in the Nusselt number, although the curvature is very close to 1. And we'll have a look at this later. What I would like to show you now is something about which we were quite surprised. Since the simulations are 2 dimensions, they are very cheap. We can do a lot of them and run them for very long times. So here's a simulation which was run for 20 viscous time units, which would be 200,000 advective time units, which is about 1,000 more than what is typically used. And what you can see is that the rolls in this space-time diagram, they are moving a lot up and down. They have big oscillations in the positions. You have very large drifts in the time. What we'll do now is we'll look at the phase. So we have here essentially, I think, 26 rolls. And what we'll do now is we'll check how they are shifting up and down in time. We do this by looking at the phase of the first Fourier coefficient, or the Fourier coefficient for this number of rolls. And you will see indeed that there are very large displacements of the vortices, up to 8 gaps, 4 down, 4 up from our reference state, which occur on the viscous timescale. We have FFTs, which I'm not going to show here, but we were quite surprised to see this. So if you run a simulation, it would be just a very short period, like the first 2 peaks, and you won't observe a displacement. But if you run for very long times, we show that the viscous timescale is actually important for the long time dynamics of the system, also in the turbulent regime. Now we want to quantify the turbulent transport. How good is the analogy regarding turbulent transport? And we are going to do a lot of simulations. So here you can see the rotation number in the x-axis, the Nusselt number. In the x-axis, we have the Rayleigh-Banach result as a reference in orange color. And you can see that for a particular rotation number chosen here, the agreement at different Rayleigh numbers is very good. So the transport is exactly the same once scaled properly. We are going to do a lot of simulations more now focused on just 2 Rayleigh numbers. And you can see that the agreement indeed is very good for a very wide range of rotation numbers for very mild curvature. And when we increase the curvature, then the agreement gets restricted to a very, very small area or point. And you can say even for curvatures which are not too large, like 0.91. And when you go a bit farther on it, what you will see is that the agreement is also only by this rotation number restricted to a very, very small range of rotation numbers. So what did we wanted to understand what's going on here, and what we decided, and this was an idea by Jose Lopez, to try to correct for the analogy. And what we did is to say, okay, we are not going to take the linear basic flow which you have in rotating plane Couette or in Rayleigh-Banach convection. We have just a linear temperature profile, a conductive profile. we are going to use the true profile of Taylor-Couette for the analogy, taking account of curvature. And when you do this, what you do is you recover an analogy which is similar to the one by Eckhart et al. But in this case, the parameters that govern it are the shear Reynolds number and the rotation number introduced first by Dubrul some 15 years back. And once you do this, so you can correct for the effect of curvature in the results, and you'll see then that the agreement is much, much better. So you can see the original analogy for rotating plane Couette in blue, which works only really well for very narrow gap. And then once you correct by using the circular Couette flow, you see that the results are very close to the Rayleigh-Bénard convection in a wide range of rotation numbers. Now, so we can conclude from this part of the talk, and I'm really coming close to the end now, so that Lorette doesn't have to stop me. For this part, we can say that the analogy works really well. So we can, the Eckhouse dynamic is fully, Eckhouse dynamics is fully recovered. The temporal dynamics is really, and spatiotemporal dynamics is really identical in the two systems. There are differences which increase rapidly as you increase the curvature, but you can correct for this effect by redefining the shear and rotation numbers. Now, we wanted to have a look also at what happens when we go to 3D flows, because that's what you have in a real experiment. And as you know, when you go to 3D flows, the streamwise direction in Taylor-Couette is very different than the span-wise. In Rayleigh-Bénard, they are identical, but in Taylor-Couette, you have a very strong convection in the azimuthal direction. And for example, if you look at the linear instability of Taylor vortex flow states, which according to the analogy are all identical, so they just have different rotations and shear Reynolds numbers, but their combination yields the same Rayleigh number, you will see that their instability is very, very different. So close to the case of stationary outer cylinder, you have huge growth rates, and as you go toward the Rayleigh line, the growth rate starts to decrease. Yeah, so this flow is very 3D unstable. The last one here in blue is 3D stable. So this means already we expect very different dynamics in 3D. And to do this, we started doing a few runs of three-dimensional Taylor-Couette flow at relatively low Rayleigh and shear Reynolds numbers, sorry. And you can see here that, however, the space-time diagrams in 3 dimensions look very similar to the 2-dimensional case. So we have sort of displacements of the vortices up and down. They are shifting in time. Superimposed to it, you will see these very fast oscillations. That's because the waving mode, or here in this case, a chaotic waving mode, is crossing your observation point several times, yielding these very fast oscillations. But you can see superimposed on it, there's also very slow dynamics of the large scales. And if you go to other flows with the same Rayleigh number, but now in 3D, you will see that the dynamics is changing a lot. So here the wavy structure is much more regular. And if you go closer to the Rayleigh line, sure enough, you just get 2-dimensional Taylor vortex flow. So with this slide, I would like to conclude my presentation and say that the exact analogy proven by Eckhart et al. Is extremely powerful. To me, it was really unbelievable that the two systems can be transformed into each other mathematically so that they are the same one. And by doing this transformation, there's a lot of information you gain about scalings that we are also looking into right now. Also to say that for very small curvature, as expected, we have very good agreement for everything we looked at, but even for moderate curvature like 0.9, the agreement is not so good. Regarding the transport, this agreement can be corrected just by redefining the parameters. And now to come perhaps to the point which was most surprising to us, this very surprising importance of the viscous timescale in the problem, so that really the large scales of these flows change on the viscous timescale, which is orders of magnitude longer than the objective timescale normally used for the simulations. Of course, in the experiment, and I think that's a key point, you cannot expect this to happen because you have end caps. And then I guess that the Taylor rolls cannot go up and down in this way. They do it in the periodic simulation. But at any rate, we were really surprised that we have this very long-range dynamics. Now, what comes next? We want to quantify this for 3D, especially taking account of the changing symmetries of the problem. It is to us very surprising that the two systems scale in the same way regarding turbulent transport, given that they are in the streamwise direction of Taylor Couette so different. So maybe, yeah, coming back to the beginning of the talk, I think, yeah, Taylor Couette flow and Rayleigh-Benach convection are indeed twins in 2 dimensions, and this was proven by Eckhart, Döring, and Whitehead, and they are not so in 3 dimensions, but we'd like to understand this in more detail. Okay, I think I'm done. I think I used my time completely. So thank you very much for your attention. I would be happy to take questions.
Well, we can unmute. Anyway, thank you very much for that. It's one of the great signs of someone that they can take something so simple and do so much with it. That was very nice, and thank you for reminding us of our dear colleagues, Charlie Doring and Bruno Eckhart. I guess we have time for maybe one question. Perhaps at the same time, we could have the setup by Harminder Singh. Please, can you share your screen? Let's see if that's possible. And so unmute yourselves, can you, to just ask questions. Don't be shy. We don't have much time.
Hello.
Can people unmute themselves? Yeah.
I just wanted to know if you could apply the same analogy using experimental data, not just numerical data. And if the results, because experimentally and numerically, you always find small differences.
Well, there's one point, which is the vertical boundary conditions in the Rayleigh-Benach system normally would impose like something like insulating boundary conditions. And in Taylor Couette flow, you have a discontinuity because of that will generate the anomalous modes and so on. So you always have vortices close to the end plate. And I think that in an experiment, the analogy is always broken before, it's always broken because of the boundary conditions. But otherwise, the rest, I think that the impact should be small and the analogy should be definitely experimentally observable if you have the narrow gap enough, if the gap is narrow enough. So this is not just a numerical toy, there is an exact analogy in the equations, and if the boundary conditions are good enough, that definitely this should be seen in the experiments. I'm pretty convinced of that.
Thank you.
So,
More questions?
Laurette, if there's time for one more question.
Yes, go ahead. One more question, please.
So it's a very nice talk, Mark, which I enjoyed a lot. So the question is on the initial conditions. So in 2D Rayleigh-Benach, things depend on the initial conditions. So the number of states which you have, the number of rolls depends on this. And you showed results for Taylor Couette. I mean, there you would also expect the dependence on the initial conditions, so that the number of rolls which are realized would affect, in fact, the Nusselt number. So did you explore that?
Yeah, this now I cannot show the slides anymore, but in a slide I had the Eckhouse band, and we tried a massive number of initial conditions and exactly we computed exactly the whole Eckhouse band, and we see that the Nusselt number indeed changes quite a bit along the band. So if you want to do the comparison to Rayleigh-Benach, you need to compare states with the same number of rolls. Yeah.
Yes, and it really matters a lot. I think it's important. I think it's particular for those at onset, it really matters quite a bit, and in particular for small aspect ratio, of course, when it's a difference whether you have, say, 4 or 6 rolls. Yeah, absolutely. I mean, there is for Rayleigh-Benach, I think you characterize it very nicely in your paper with Olga. And we were also surprised. I mean, it carries over to the turbulent regime so massively. That's really, yes, it's a very important point. I agree.
Okay, so now we will stop the questions. There's still some questions in the chat, and so Mark can answer these questions in the chat when he gets off. And now we will go to Harminder Singh from the group at Le Havre and LOMC, and he will talk about the law of the wall. Thank you.
Thank you, everyone, for this preparation of this ICTW. And thank you for Mark for such an interesting presentation.
Hey, can you go closer to your microphone, perhaps?
Okay, hello.
Yes, okay, that's better.
Okay. Okay, I'll just start. Today, I would like to present a new approach towards the log law of the wall in the Taylor-Couette system at the intermediate Reynolds number. As Laurette explained, I work at LOMC in the Université Le Havre. So I will start with a small introduction, presenting what the basic objective of this presentation is, and present the log law, and then the results, and finally the conclusions. So if the classical log law works optimally even in the Taylor-Couette system at high Reynolds number, as shown by the 2 million Reynolds number by the Sander-Huisman, even in the inner and the outer boundaries. But at the lower Reynolds number, or we can say the Taylor's number that they have presented here, the relation is not that similar. It's far away. It's not optimal. So at intermediate Reynolds number, the Taylor-Couette system, the deviations are significant compared to the classical log law. Based upon this, so I presented a new log law when I was working at INSA Toulouse, in which we considered that the log law is not linear, but rather quadratic, which I will present today. So, and which behaves non-linearly with the radial distance as a quadratic function. So the objective of this study is that I would like to generalize the two constants. That one is the mixing length constant, which is used to prepare this new model based upon the turbulent mixing length. So one is when obtained by integration of the mixing length equation. Then the second is once we integrate the Rance momentum equation, we obtain another coefficient. So if the idea is if we can generalize these two coefficients for this new model. So first of all, the basic necessities for this model to function is that the Taylor-Couette system for the two concentric cylinders, outer cylinder is stationary and only the inner cylinder rotates. And in that, after a certain Reynolds number, when we reach turbulent Taylor-Couette rolls, in that we work with a specific profile, azimuthal velocity profile at the center of the Taylor rolls, or perhaps an axial mean over a pair of Taylor vortex. So what I mean is at the center is when we are in the center of this Taylor vortex roll, or mean of a pair of this Taylor vortex. The question is why at this center of Taylor rolls? Because to derive the equation, we suppose that radial and axial components of the velocity are negligible to simplify the equation, and both are negligible when we are at the center of this Taylor cell. That is the main reason, and this law functions when we have these conditions. And secondly, we need good estimation of the torque, or we can say global properties, for the optimal functioning of this new log law. So after simplifying the Rance equation, we can obtain the equation 1, where we have the E star, which is based upon the torque or the average torque. So it is an average torque, and it's not a local torque for the profile. And then we can say that the viscosity, turbulent viscosity, as introduced by the Prandtl, we can specify, and after the integration, we can obtain this CLM constant separately for the inner wall and the outer wall. But the constant remains similar, even if it is an inner wall or outer wall, constant remains similar for the whole geometry, irrespective of the rotation rate. So it is more of a geometric specific coefficient. So once we insert this mixing length in the Rand's equation, we can, after integration of that, we obtain this presented U equation, which is quadratic in nature. So if we present the mixing length profile, we can see in the starting region presented for in this I present for 4 different geometries: the T3C 20 turbulent Taylor Couette geometry, the data which was provided by Sander Huisman, and the data that I obtained at INSA Toulouse, and then the data that I obtained through the graphs of Kobayashi, and then there is a DNS data which I worked with Viviana while I was working in Brazil. So for these 4 geometries, I have different eta. So that was critical to have different geometricals, how it will, if it is possible, so that at different eta for different geometrical conditions. So if for these 4 different geometries, I present the velocity profile and the velocity profile that is obtained experimentally or numerically, and the model that I just presented, how it fits with these data. We can see that the model works very well within at the Reynolds number that have been tested. So in terms of generalizing the model, we can see as the eta it becomes smaller, the mixing length coefficient becomes larger, while the coefficient for the velocity profile increases linearly with respect to the rotational rate of the inner cylinder. This is a quick presentation because I do not have many geometries. So, but for the 4 tested geometries that I presented here, it functions pretty well for this model. But it is more geometries are required at different geometrical conditions, different eta values. So to see how it works, there's a results of van der Veen, which is at eta of 0.5, but I have not been able to apply it yet. And then the problem, one of the biggest problem is that it is specific to a velocity profile, that it has to be in the center of the Taylor vortex pair, or a mean profile of vortex pair. And we need torque data for these to make it function. I have tested this within 3,000 Reynolds number to up till 200,000 Reynolds number as obtained from the data of Huisman. On the other hand, more recently, Bergu et al. Group has presented a new velocity profile, presented rather a curvature correction to the azimuthal velocity profile using the Obukhov length scale, which fits all eta and all Reynolds number. So if we can see, this was the data, actual data of the velocity profiles of the Sander Huisman. And once they provided the correct curvature correction through this LC Obukhov length scale, they were able to follow the log law profile, the classical log law profile. So this object, so these two methods are different to each other. One is provides a curvature correction to the azimuthal velocity profile, and the one that we presented follows the actual velocity profile and presents a new log law. Maybe hopefully both of these methods can find their space separately in the scientific community. Thank you for your attention.
Thank you very much. We have time for a few questions. Now, I know, let me just say some things before. I know we don't have nearly so much time as we would like for questions. I see a lot of chatting going on about Mark Avila's talk, and so you're welcome to follow these chats. But we will also be having during the break, we will have that in a Wonder Me room where people can meet and chat. And we want to encourage everyone to go to that. It might be a new experience for you, but you just have to click on a link and then you can ask your questions of the speakers in person. You can join little groups. I hope that you'll find it not too different from interacting in person, possibly even better for those who are shy, maybe. So you'll get a chance to talk with the speakers and with each other very shortly. Are there questions for Harminder Singh? I think just ask them out loud, please. I don't think we have time for anything too formal, or maybe ask them in the chat or something about the law of the wall.
I have perhaps a question. How is counter rotation, let's say, is it also in your model?
No, it's presented just for the inner cylinder rotation.
But is it adaptable, let's say, to also allow for that, or is it that still a challenge, let's say?
I've not tested because I do not have data for.
Yeah, I can imagine this data is very scarce indeed.
Yes, if I have the data, maybe I can start testing for the counter rotation. I just recently got back to this work, and just before I had two geometries, my Insatulus and your geometry. But yeah, I started working this year. I said maybe I can try to maybe more generalize it. So I worked out around two more geometries. I will try to formalize this one with at least 7-8 geometries. Then if I have the data for co-rotation or maybe counter rotation, then I will definitely like to try and see if it works.
Yeah, this data is indeed very scarce indeed. Well, at least we don't have a plan yet to measure this anytime soon, but maybe some other groups or people who are watching now.
Can Pimbuli, the next speaker, share his screen, please? And we can keep asking questions of Mr. Singh. Can you there? Thank you very much. Okay, so we know we'll be able to start on time. More questions about the law of the wall, perhaps? You can just speak up, or you can ask. Okay, well, then. Okay, well, we anything? No. Okay. Well, we thank you for your talk. And I hope we'll see you in the Wonder Me room for more questions. And now we have another talk from jointly from Twente and München and Melbourne, just as befits our international field, about characterization of rough surfaces in turbulent Taylor-Couette flow. Please begin.
Yeah, thank you for the introduction. So my name is Pimbele, and as you mentioned, this is indeed a work combination of collaboration of 3 universities. Right now, I am not affiliated to any of these universities anymore, as I'm working as a postdoc at the NTNU on turbulent channel flows in Trondheim. But this still dates back to my time as a PhD candidate in the physics of fluids group. And this work has recently been published in JFM. So I added a little QR code here that links you to the paper. And during my PhD, we started to find out how we could attach coatings to the inner cylinder of our Taylor-Couette facility. So they started with hydrophobic membranes, and later we also started doing this with sandpaper surfaces, because we wanted to contribute to the field of roughness research. And roughness is, of course, omnipresent. So we find this on the rusted inside of pipes, of connections like rivets and bolts on all kinds of plates. and of course also as fouling that grows on the hull of ships. And one of the pioneers in this roughness research is Nicorazze, who combined very well-defined sizes of sand grains with pipe flow to study turbulent flows over rough walls. And he found already that the log law that we find in turbulent boundary layers is preserved, so the same gradient defined by the von Karman constant kappa, but with the offset in the velocity, a roughness penalty you can call this maybe. And this is nicely illustrated in this work by Vlak and Schultz, where they use a boundary layer facility. And we see here a nice log law on a smooth surface that shifts downward with increasing roughness. And what everyone does in this field is to relate their results back to the original sand grains of Nicorazze, so to say, using this fully rough asymptote, where this Ks is the equivalent sand grain roughness, which translates back to the original work of Nicorazze in 1933. So all these kind of characterizations are typically done using boundary layer facilities, where people use PIV to measure velocity profiles, and then use a Clauser fit to get the friction velocity U tau. So when we look at our own facility, the Twente turbulent Taylor-Couette facility, we know that the Taylor-Couette geometry is mathematically well-defined, but also that from torque measurements, we can directly get this friction velocity U tau. The downside maybe is in this, that the walls are obviously curved. So one very valid question is then, how valid is this log law still over a curved surface? So this plot by Huisman and all, well, it's the second time at least we see this today, so it's becoming rather famous maybe. But he showed already that in a considerable range, this log law identified by the gradient of the kappa von Karman constant is still valid. And then in 2020, Berghout took this a step further and identified actually two regions within this log law. One region where turbulence production is solemnly the result of shear effects, and another region a little bit further away from the wall, where the curvature of the wall also starts to play a role in the production of turbulence. So when we look at the equations for the production of turbulent kinetic energy in cylindrical coordinates, and we say that local production equals dissipation, we see these two terms arrive. So one clearly relates to effects of shear as the gradient of the velocity profile. And another one here is related to the effects of curvature that contribute to the production of turbulence, which relates to the momentum, constant momentum in the flow. And the ratio between these two terms give a length scale we call the Obukhov length scale, which defines the boundaries of this region, which where both effects of shear and curvature play a role for the production of turbulence. Now the question is, if when we are not looking at smooth walls but at rough walls, if we still find this constant shift in angular velocity in this region as well, so in this extended log law region or modified log law region, how you can maybe call this. So what we did, we covered the inner cylinder of our Taylor-Couette with sandpaper that we have very well characterized. And we set up PIV to measure the velocity profile inside the boundary layer. And we also measured the torque required to rotate the inner cylinder at a constant frequency. And the outer cylinder is stationary at all times. And so in here we find that with increasing roughness, we see indeed this shift in angular velocity for increasing roughness. And then when we look at this region where both shear and curvature play a role, we see that this shift in angular velocity due to the roughness, this roughness penalty as I called it before, is constant. And And then when we fit this data on top of the original fully rough asymptote of Nicolas to compare these results and find the equivalent sand grain roughness, we see that this nicely this falls nicely on top of this. And then when we look at this equivalent sand grain roughness we get from fitting, this is very similar to what we know the equivalent sand grain roughness to be from measuring the surface directly. Now, the interesting question is, of course, can we just do all of this also without doing PIV? Because we know now very well what the velocity profile in the boundary layer looks like. We can define these boundaries using this Obukov length scale. I mean, when we look at this a little bit closer, we see that for the short term, the gradient of the velocity profile, this can simply be set equal to just the shear velocity or the friction velocity and the von Karman constant. And when we look at U over R, so the contributions of curvature in the production of turbulence, we can approximate this by the angular velocity of the inner cylinder. And then this term LC, we can simply get from torque measurements, from which we know the friction velocity, and kappa and omega I, the rotation of the inner cylinder, we know, of course. Then the remaining question is, what happens in the bulk region of the flow? So because we know for smooth walls already that we have constant angular momentum in the bulk, but this is also the case for rough walls, because if this is the case, we can use a matching argument between the velocity profile of the bulk and the boundary layer. So when we look at some plots of the angular velocity in the full gap between the two, the inner and the outer cylinder, both for smooth inner cylinder and rough inner cylinder, we find that we find indeed this constant angular momentum for smooth walls, but also for rough walls. So this means that now we have all the pieces of the puzzle complete, and we can match the edge of the boundary layer with the bulk, just like Cheng did. But contrary, we don't need a fitting argument to do this, because we can use our Obukov length scale, LC. And this LC we can get from the torque measurements we do, which gives us the friction velocity. And then, well, LC gives the edge of the boundary layer, and we can match the edge of the boundary layer to the bulk region of the flow. And this also works for rough walls. So here we see results for smooth walls and rough walls, where we compare experiments through this theory. And we find that for both, well, we see that for when we plot it as Nusselt versus Taylor, we find a nice agreement, but also when we plot it as a friction coefficient versus the Reynolds number. And then the interesting question is, of course, how does this compare to the results for the equivalent standard grain roughness that people find using the more traditional way, so to say, using boundary layer facilities and particle image flow symmetry. So here we plot the equivalent sand grain roughness, but also the skewness of the roughness distribution of the sandpaper that different people use, because this also actually plays a role in this. And we find the empirical relation from Fleck and all that incorporates this skewness and different data points. And we find that when we use the exact same sandpaper in our Taylor Couette as Todd Squire did, we find a nice agreement. And also when we have the same grid size, but well, not the exact same sandpaper, we find nice agreement here. So from this, we say that from torque measurements only, the Taylor Couette can be used to characterize roughness. And with that, I would like to thank you for your attention, and I'm ready for taking questions.
Thank you. This last observation of yours reminds me of the original purpose of Taylor Couette flow, which was to measure viscosity.
Yeah,
right?
exactly.
And so here you can use it to measure roughness, and so that's a nice, nice, interesting application. Kind of backwards from our. I mean, we no
Yeah.
longer use Taylor Couette very much that way. We use it. We assume things and then find out, rather than getting data to so as to learn about the experimental properties. So we have time for questions now. Um, um, can you just speak up? Or if you want, you can write your question in the chat or raise your hand or something like this. Well, okay, I will ask something first, a small thing. First, I saw that your LC seemed a kind of version of Y. It seemed not a constant, but a coordinate. Am I right? And then it switched to being a constant?
Yeah. So it's, I think, where did I find this version? I think here I put it, right?
Mm-hmm. Yep.
Yeah, exactly. And then later on, this Y is gone. Yeah, exactly, because then it translates to a physical length.
Okay.
So now it's just, yeah.
You chose a value for Y, say, or something. Or no.
No, no. So it's just this.
Hmm?
No, sorry. You wanted to ask something.
Oh, no.
Okay.
Okay. Other questions then? Well, let's see. I can continue asking. Is there such an idea as asymptotic roughness? There isn't, or is there? Or can you just keep getting rougher and rougher?
Well, so there are of course some limitations. So you cannot get too rough. Your roughness height should not exceed a certain length scale, because then it will directly influence the shear and curvature region. So you need to have a certain separation of length scales. You can, yeah. So there's an upper limit to the roughness you can use, or yeah, you can characterize using this.
May I ask Dr. Gredanos to share his slides, please? And we can continue asking questions while sure that Mr. Gredanos can start at the right time. Okay. Are there more questions then on this roughness talk? I remind you that you'll be able to interact with each other and with the speakers during the upcoming break, just after this next short talk. We'll have a half-hour break in the Wonder Me room, which I will even now put on the chat. Okay, so I guess you could start. This is from the Delft group, am I right?
Yes, that's correct.
Yes, the Delft group. Another Taylor Couette and turbulence work. I guess you can start. Thank you.
All right, thank you. Good afternoon. My name is Arnold Gadanis, and I will discuss our work about scaling and riplet drag performance under periodic-driven Taylor Couette flow. So this work is indeed done on the fluid mechanics lab in Delft, in the lab of Professor Westerwill. So in the 80s, most research on the riplet drag reduction started with some early publications of Walsh and Beggert. And so on, there was a lot of riplet drag reduction research done on steady flow conditions. However, when the flow starts to oscillate or is unsteady, where an oscillating velocity superimposed on the steady velocity delivers very interesting and complex fluid dynamics. Also for the drag reduction case, it's not often clear what the drag reducing effect will be maintained, and that's the question in this study, to see how much is maintained under the unsteady flow conditions, and also what is the interesting relation between the drag reducing solutions under unsteady flow conditions. So we use the Taylor Couette facility to investigate oscillating flows and also the drag reducing effect of ripplets under oscillating flow conditions. So the Taylor Couette we use has a gap ratio of narrow gap with 0.92 and an aspect ratio of 22 with all the other dimensions put in this table here. So the experimental consideration that we have, we perform our experiments under exact counter-rotating conditions, where we have the inner and outer velocity of the cylinders in opposite direction, but in the same order of magnitude. So the inner cylinder velocity can be put as a sinusoidal function, where the delta ui and delta uo is the amplitude on top on the time average velocity. Also, the inner and outer cylinders operates in opposite direction, and it gives a certain shear velocity, where the velocity is under the can also be put as a sinusoidal function, where the relative amplitude is given by the amplitude of velocity change in contrast to the time average velocity, and can be made can be normalized into this function. So if we look into the scaling parameters in static conditions, we have the good old shear Reynolds number, which gives us the internal forces against viscous forces, and we see that the drag the power to overcome the frictional drag can be scaled by the angular velocity times the wall shear stress. Also, this wall shear stress scales to the function of the friction coefficient times the shear velocity squared, and for moderate Reynolds numbers, you see that this power to overcome the frictional drag can be scaled to the shear velocity 11/4. However, on the periodic or unsteady conditions, we have two extra scaling parameters, which is the oscillatory Reynolds number, which gives the additional inertial forces over the viscous forces, and the Wormsley numbers, which gives the transient inertial forces over the viscous forces. For a quasi-steady state solution, when the period time is very large, we can calculate the power to overcome the frictional drag by this integral. However, when the period time becomes smaller and smaller and the Wormsley numbers becomes larger, it's still unknown what the power becomes. Only we can say that it's a function of the three scaling parameters stated on the slide. So for our experimental outline, we divided in two parts. First of all, we studied the effect just for oscillating flows, so for without ripplets. We have two cases, a high Reynolds number case and a low Reynolds number case, with different operating conditions for the oscillatory Reynolds number and the Wormsley number. And on top of both cases, we also performed a semi-quasi-steady state, where we take a period time of 10 minutes to get a Wormsley number around 1. We can compare those values with the analytical solution that can be calculated by this integral. The second part is where we really try to see what the efficiency is of ripples under unsteady flows, and to make sure that we can reduce or avoid the rotation effects, we apply ripples on the inner and outer cylinder surface. The riplet surface that we have are triangular riplets with the dimensions stated here. So the first results that I show you here, so on the part 1, we see the effect of oscillating amplitude. When the amplitude is still very small, we almost see no any change in the drag change, where the drag change is can be stated as the time average drag under these conditions compared to the same shear Reynolds numbers under steady flow conditions. So the steady flow conditions are stated here with an amplitude of 0. For very low, you see that there is almost no change in drag, in frictional drag, which is caused to the marginal change in turbulent fluctuations in the flow. And so the general turbulent fluctuation on the steady flow conditions remains dominant. So the change in amplitude is smaller than the turbulent fluctuation of the flow, which can be considered as 2-3 times the shear velocity. When the acceleration becomes more violent, you see that the drag change increases, where at 40% of amplitude even goes up to 25%. So that's the effect of the change in amplitude. If you look into the change in period time, you see there are multiple amplitudes plotted in this graph, 40%, 30%, 20%. You see when the Wormsley number is very low, so that means very large period times, you see that it's indeed close to a certain analytical solution. That can be seen here. Here, this is the experimental values, the drag change, and this is the theoretical value determined by the analytical solution. So we see indeed there is the analytical solution really a function of the amplitude. When it increases, you see also the drag is increasing. So these two, this is a case for the higher Reynolds number. So indeed, we did also for the lower Reynolds number case. And you see in these contour maps, we plotted the two scaling parameters, the amplitude and Wormsley number. You see there is for the higher case Reynolds number and the lower case Reynolds number, there's almost a similar contour plot of this change in drag. So if you look into this scaling, if you try to scale, see if there is some general scaling, we start with the velocity, the derivative of this shear velocity, when it comes to the acceleration, and when we make it long-dimensional, you see that there's indeed, it's in a function, the acceleration can be put as a function of the Wormsley number and the amplitude. So if we replot the same results from the last, from the higher Reynolds number case, you see there's indeed the drag change is a relation of this amplitude, and it drops on one line when we subtract this analytical solution of the drag change, as you can see here. So the drag change is indeed subtracted by the analytical solution, and then what remains is there is only the drag increase is only a function of this acceleration term and then the scaling factor. So the second part, so also this was for the high Reynolds number case. If we plot also the low Reynolds number case, where we could go up to higher amplitudes, you see it drops indeed on one line, which suggests there is a general scaling between this drag increase and these scaling parameters that were mentioned a few slides back. So the second part are the results where we try to see what the effectiveness is of the riplets under oscillating flow. We first redid steady flow conditions to see if the inner and outer cylinder, when they were coated with riplets, are indeed giving the same results if we only coated the inner cylinder. And we see that there is indeed a drop on an identical line. If we start to do the actual experiments with the amplitude shifting to the left to the right, to the left to the right, we see that we can determine what the effectiveness of the riplets are still maintained. So and that is done in this plot. So the gray line over here is when we consider quasi-steady state. So if you only take the results on this plot and we indeed take the average of the changing Reynolds number here, we come on this gray line. However, in the actual experiments, we have a Wormsley number of 14.5, which was a period time of 3. And we see that the effectiveness of the riplets is reducing when the Wormsley number is increased. So that is considered as an increase due to the surface roughness of the triangular, I would say the triangular lipids produced into the fixed sublayer, and which gives a certain surface roughness. And this even suggests when the Robinson number is even increased, there is a certain moment that the ripples gives a drag increase instead of a decrease. But this still needs to be validated with some additional experiments. So if I may conclude this talk, for low amplitudes and moderate Robinson number, we see that the general turbulent fluctuation remain dominant. And for the quasi-steady state, we see also that the experiment results meets very well the analytical values. Concerning the scaling, we see that the drag change on oscillating flow conditions see that it is a function of the amplitude, and an acceleration where we also multiply it with the scaling factor. And riplets see that still drag reduction is possible, but the efficiency declines with moderate acceleration, and even with very high acceleration, it might even induce the drag significantly. So with this, I want to thank you. And if there are any questions, I would like to answer.
Thank you for your contribution from your productive group. Again, I think we don't have to be formal. Anybody have any questions to ask?
Yeah, I have a question. Maybe just a silly question. Are the riplets, let's say, azimuthal or axial?
Yeah, so the riplets are in azimuthal flow direction indeed. So
Okay.
they are in the flow. They are aligned with the flow, rotating flow. Yes.
Yeah. So then, because then locally you get basically points where you see, if you do full symmetry, that you see that kind of at the tips of these riblets, you see like well, convective flow, let's say.
Yes, I know the publication. There is indeed some convective flow from the tips from the riblets, but at this moment I don't. So you suggest that when you do oscillating flow, it might become worse, and with that decline the effectiveness of the riblets.
Yeah, so I think our group, we made a paper some years ago.
Yes.
Also on that, but it was not periodic; it was just rotating. So this is of course very different again. But I guess philosymmetry will be hard in your case, right?
Yeah, well, for this case it is, because we add a foil on the also on the outer cylinder.
Yeah,
case,
exactly.
and
Yeah.
you cannot look through the foil. So then we should go back to the only riblets on the inner cylinder. But that gives another problem, which was discussed in our paper, experimental fluid paper 2015, that you get rotation effects of the riblets.
Okay.
So if you only modify one surface, you get a certain already, and you have a drag reduction, then you also rotate your fluid differently, and that also gives already an additional decrease in frictional drag.
Okay. Thanks.
Are there other questions? Please just join in as turn on mute and let's see. So, well, I can ask an ignorant question. From your recent two back and forth there just now, the way I understand, so the difference between riblets and roughness is that the riblets are oriented, riblets have a length then? So, I mean, because Sander asked whether they were azimuthal or axial, unlike the roughness, which is just point particles, whereas riblets are kind of one-dimensional objects.
Yeah, so so riblets on themselves are of course three-dimensional, but they are aligned in azimuthal direction. And what I mentioned is when you are having a very violent acceleration, deceleration of your flow, you will get a certain moment that the added turbulent fluctuations will be seen by the riblets, and the riblets start to protrude through these viscous boundary layer.
Okay, thank you. So
for those who want, I can try to show them in the camera. This is a large-scale model that we used it in very viscous fluids. Can you see the triangles?
Go down a bit, down, 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 down.
Yeah,
There, yes. Okay.
So,
Uh-huh.
so they're like this, one-dimensional, and of course, kind of.
Right, right. I see, I see. Okay, thank you.
Thank you, Renee, for the presentation.
Good. I'm glad I gave us the opportunity to see, and you showed us this nice thing. So now it's time for the social event. If you go to your chat, you will see a place to click, and so just click there. You can keep your Zoom on, and you will find yourself in a room with other people, and you'll try to learn how to navigate and see everybody. Especially the speakers from this morning should go, because this will be an extra time to ask questions of them. And so see you soon in the Wonder Me room. As I say, I hope we'll be able to take advantage of the possibilities there. Thank you. See you shortly. We have the same Zoom session for the rest of the conference, as you know. Okay,